Rudolf Diesel obtained the German patent for developing the idea for the diesel engine in 1892. An early example is shown here. His objective was to create a very highly efficient engine, and he succeeded by developing an engine with a theoretical thermal efficiency of 75.6%. Gasoline engines had been invented earlier, in 1876, but at that time they were very inefficient. There are two main differences between the gasoline engine and the diesel engine. They are: firstly, while the gasoline engine takes in a mixture of gas and air, compresses it, and ignites the mixture with a spark well before top dead center, the diesel engine takes in just air, compresses it, and then injects fuel into the compressed air as the piston reaches top dead center. Thus, it's the heat of the compressed air which ignites the fuel spontaneously, rather than a spark plug. The lack of a spark ignition system in the diesel engine is a big factor in increasing its reliability. Gasoline engines generally use either carburetors, in which the air and fuel is mixed long before the air enters the cylinder, or fuel injection, in which the fuel is injected into the inlet port of each cylinder just prior to the induction stroke. Modern diesel engines, especially those used to power aircraft, use direct fuel injection, which means that the diesel fuel is injected directly into the cylinder. The injector on a diesel engine has to be able to withstand the much higher temperatures and pressures that it experiences inside the cylinder, and yet still deliver the fuel in a fine mist exactly when it's required. The second big difference between a diesel engine and a gasoline engine is in the injection process. As previously stated, most automobile gasoline engines use a fuel injection system or a carburetor, rather than direct injection. In an automobile engine, therefore, all of the air-fuel mixture is fed into the cylinder during the induction stroke, and then compressed during the compression stroke. It's this compression of the fuel-air mixture which limits the compression ratio of a gasoline engine, because if the engine compresses the mixture too much, it spontaneously detonates, which is grossly inefficient and can seriously damage the health of the engine. As was stated earlier, the diesel engine compresses only the air. Thus, the compression ratio can be much higher. The higher the compression ratio, the greater the power that is generated from a given quantity of fuel, and the higher the thermal efficiency of the engine. Whereas a gasoline engine compresses the air-fuel mixture at ratios of between 8:1 to 10:1, a diesel engine, which compresses just the air, works at ratios which can range in different engines from 14:1 to as high as 28:1. The higher compression ratio of the diesel engine leads to much higher thermal efficiency. There are problems associated with starting diesel engines from cold, and because of this, some of them utilize glow plugs. Glow plugs are required because the compression achieved in a cold engine may not raise the temperature of the air high enough to ignite the fuel. The glow plug is essentially an electrically heated coil. Once the engine is warm, the glow plugs are no longer needed, and they are turned off. There are two types of glow plug in use, the metal type and the ceramic type. Metal-type glow plugs have their heating coils mounted in a heat-resistant alloy tube. Ceramic-type glow plugs, which have been employed in diesel engines since 1985, have their heater elements contained in a ceramic material, which is made of silicon nitride. Because of this fact, ceramic-type glow plugs have a greater heat resistance and durability. There are two types of fuel injection system which are used in modern light and medium-powered diesel engines. They are the direct fuel injection and the common rail fuel injection systems. We'll look at the direct fuel injection system first. Most light-duty diesel engines use an engine-driven in-line pump to distribute fuel under high pressure to each of the injectors. The injectors are situated in each cylinder head. They are mechanically operated and have spring-loaded poppet valves, so they pop open and spray fuel when the fuel line pressure exceeds a certain limit, typically 4,500 psi. Electronic controls on late model injection pumps regulate injection timing, fuel mixture, and idle speed. The purpose of the fuel injection pump is to deliver an exactly metered amount of fuel, under high pressure, at the right time to the injector. The injector, unlike those fitted in a gasoline engine, which inject the fuel into the intake manifold just before the inlet valve, injects the fuel directly into the combustion chamber, or in some cases a pre-chamber, which is connected to the cylinder. The injection system that delivers fuel to a diesel engine operates at much higher pressure than a gasoline injection system. It can be as high as 17,400 psi for a direct injection system, and up to 23,500 psi for common rail systems, compared to 35 to 90 psi for most gasoline fuel injection systems. Another function of the fuel injection pump is to regulate the timing of the fuel pulses. The timing of the fuel pulses is adjusted in response to engine RPM. Because the vane transfer pump or low-pressure feed pump, which pulls fuel from the tank to the input of the high-pressure section of the pump, is driven by the engine, at higher engine RPM, its fuel pressure output is higher. These fuel pressure changes are used to either advance or retard the timing. There is also a cold start device, which advances the idle timing manually. A mechanical governor, also fitted to the fuel injection pump, limits the maximum speed of the engine. A magnetically operated valve or solenoid opens and shuts off the fuel channel between the feed pump and the metering pump. An air inlet pressure sensor is used to determine the maximum amount of fuel delivered on injection pumps for turbocharged engines. On newer, normally aspirated engines, a similar arrangement is used for altitude compensation. The second type of fuel injection system is the common rail. The common rail fuel injection system is designed to supply constant fuel pressure to electronically controlled injectors from a shared fuel reservoir. This means that the engine fuel supply is not dependent on engine rotational speed. A common rail system is built around four basic components. Firstly, a high-pressure pump with a pressure regulator and an inlet metering valve. Secondly, a rail or fuel feed, which contains a pressurized reserve of fuel. Thirdly, injectors, which inject precise amounts of fuel into the combustion chamber as required. The injectors can be either solenoid-energized valves or operated by piezo crystal. In some circumstances, they can be actuated up to 25 times a second. Finally, an engine control unit, the brain of the system, which precisely controls the flow and timing of the injectors, as well as the rail pressure, while continuously monitoring the operating conditions of the engine. Simply explained, the term common rail refers to the single fuel feed line, from which the individual feeds for each injector are taken, on the common rail direct injection (CDI) engine. Whereas conventional direct injection diesel engines must repeatedly generate fuel pressure for each injection, in the CDI engines the pressure is built up independently of the injection sequence in a high-pressure pump with a pressure regulator and inlet metering valve. This pressure remains permanently available in the fuel line. The common rail, which contains a pressurized reserve of fuel, is upstream of the injectors in the cylinders. It acts as an accumulator, distributing the fuel to the injectors at a constant pressure of up to 1600 bar. Mounted in the cylinder heads, fuel injectors, which are really high-speed solenoid valves, inject precise amounts of fuel into the combustion chamber as required. An electronic driver unit controls each injector's opening and closing. This procedure is regulated by the electronic engine management, the brain of the system, which separately and precisely controls the injection timing, rail pressure, and the amount of fuel injected for each cylinder. It does this by using information obtained from continuously monitoring the operating conditions of the engine. Sensor data from the camshaft and crankshaft provide the foundation for the electronic control unit to adapt the injection pressure precisely to demand. Fuel pressure generation and fuel injection are managed totally independently of each other. This factor is in itself an important advantage of common rail injection over conventional fuel injection systems. Common rail direct injection also offers distinct environmental advantages, with enhanced combustion efficiency leading to reduced exhaust emissions. The system produces quieter, smoother operation over comparable engines with either direct or indirect fuel injection.